Are there any questions? Anybody have any questions? I've tried to grade up through 13 and get as close as I can to being done with grading to there. There are a couple of you I got a couple of already through 26. So if you need me to turn on the final exam, let me know in Netacad and I'll go ahead and turn it on for the next 7 days. Actually, I'll go do that right now just in case somebody needs it. But I was fairly shocked. I went to grade it and I was looking, I was like, good gracious, I got some people already up in lab 26. So you've got some overachievers in your class here. But the other thing I want to show y'all real quick, I just noticed this. It actually happened last week, I believe, but don't freak out. You'll notice that in Netacad, when you go into teaching and you go into one of your classes, so here's our ENCORE class, you'll notice that the outside looks different. It's like they've went ahead and moved to the new interface for this portion. But as soon as you go into the actual sections, it's the old look. So if you go in here, it'll be the old look. This won't be because we don't have, there's no content in here, but in a class with content, you'll see that only the first page looks like that. So you'll see it looks like this looks totally new, which is going to be some of what our new, everything will look like after we get into the new system after convergence. But as soon as you were to click into the course content, you'll notice it flops directly back to our old LMS look. So it's nothing has changed on that. It's just on the outside edges. That's what it's looking like. So
They changed some of the icons too.
Yeah, they've changed the icons exactly. Yeah. So it looks like they've done it on the main page, but once you actually drill into the content, right now the content is still in the same format. And it should be that for any classes you create before convergence, they'll have this as their landing page, and then the content will still be in the old LMS look like this. But any class created after convergence, which is happening, the 22nd, 23rd, 24th, 72 hours there. Anything after that, you will have both this new landing page and the new way for content to look inside of the class. So I have the new skills for all. It won't have this old look to it. So just be aware of that. I didn't want you to get surprised by it because it's nothing really major, but it's when you first log in, you're like, whoa, it's all changed. And then you dig deeper and you're like, well, it's not that different. So still no major thing there. So I'm gonna actually go turn on the final exam and course feedback, make sure it is on for the course feedback will be on for the next 30 days. And then the final exam will be on for 7 days. And if anybody needs it after that 7-day window, just send me an email and I will turn it on for you. So we obviously are on the brink of our July 4th break. So we'll get started and get going here if no one has any questions. All right, let's talk multicast. We're going to talk about some fundamentals. We're going to talk about addressing. We'll talk about IGMP, and we'll talk about PIM. That's where we're going to go today. We're going to talk first about what is multicast. It is one of the 3 different types of communication we can have. We obviously know about unicast, which is one-to-one, broadcast, which is one-to-all, and multicast, which is one-to-some. So we've talked about multicast, and we've used multicast in the past because we know it's used by a lot of our routing protocols. It's used by EIGRP, it's used by OSPF, but we have not really talked about how a multicast stream can be used in a modern network. So here is a basic multicast architecture where we have a multicast source, which could be, no problem, Chris, which could be anything from a video stream to real-time or as near real-time stock trade and information as you can get, but something that needs to go to a group of people in your network. And you really don't want to broadcast it because it would use up too much bandwidth, too many resources. So we'll notice here we've got a thing called multicast traffic using goes to the first hop router. We then have protocol independent multicast, which we will talk about, which rides on other routing protocols, which allows you to create different types of multicast setups to allow for multicast to be sent in your network. You have a local multicast router, and then you'll have what's called an IGMP or Internet Group Management Protocol query and a layer 2 switch that could be an IGMP snooping switch. And then finally, you've got your device, which is going to be running some kind of program, which will have it join a multicast group. So we'll talk a little bit about we'll talk about all of these items as we go through here. So here again is our typical communication we've talked about. Unicast, which is not bad. Broadcast, which can be bad, but we can't obviously turn all broadcasts off. And then multicast, which is a better way to do broadcasts if we can make it work. So here's a unicast video feed. If you did it and you had to send it to 10 workstations, you would have to create 10 different feeds, one to each workstation, which is highly inefficient. All right. The only good news, I guess, about this unicast feed would be that it is possible that workstation F, there will be no feed going in it, so it's not going to have to actually look at any traffic coming to it. You could do this with a broadcast, but if you do this, it would go to every single workstation, including F, and then F would have to discard it after the CPU goes all the way up and figures out, hey, I really am not part of this group and don't want to see this video stream. So we're going to do the best of both worlds. And what we're going to do is we're going to create a thing called multicast. So we're going to create a way for the routers and switches in your network to send this multicast traffic only to the particular host that want it and need it. And so we're going to do that in many ways. Now, depending on what type of multicast you're running, it could be that workstation F actually does receive the multicast and then has to discard it. But if we connect it to a switch that has IGMP snooping on it, we can actually set it up to where it will not receive the multicast at all. It will be able to be ignored. It won't even send it out the port that F is on. But we'll talk about IGMP a little bit later. So one-to-many communications, all right, down this multicast distribution tree. It uses special destination IP addresses, which are based upon the multicast range of 224 to 239, which is Class D, if you remember old Class Ds. It still only has to send one stream in one session, and then devices selectively request that stream. All right. Now, Cisco telepresence, real-time video, IPTV, stock traders, distant stock tickers, all these, including up to gaming, can use multicast. The problem with multicast is it's very difficult for multicast to survive the internet, so this will be pretty much inside your network only. Once you get outside of your network's boundaries, unless you've got a really weird setup with your ISP, multicast is not going to survive out past your edge with the ISP. You might can put it inside of a tunnel, but otherwise, this is basically on your internal network. So what is multicast addressing? Again, it's Class D, 224 to 239. And you'll notice that all of it starts with 110, and that is because to be a number between 224 and 239, the octet must begin with 110. So 110, 0000 is 224, 110, 1111 is 239. So that if you ever wondered why it has to begin with 110, that is because of this Class D range. So here we have some different setups for the multicast range. Local block, they are used for protocol control traffic, not forward out the broadcast. And then we got others that can be forwarded through the internet. Again, depends on how that's set up inside your connection with your ISP. Here's some well-known reserved multicast addresses. Obviously, 224.0.0.5 is all OSPF routers. 224.0.0.6 is all DRs. 224.0.0.9 is all RIP. 224.0.0.10 is all EIGRP. And those are pretty much the ones that we know. There are some others in here. We'll talk a little bit about this Cisco Auto Rendezvous Point 39 and 40. Those are there, but we've seen some of these before in the past. Okay. So one of the big things about multicast is it takes an IP address and it has to convert it into a MAC address that the host will then listen on. So there's an easy way to do this. First off, all multicast address MAC addresses will be 01005E. They will start with that, 01005E. And then whatever the IP address is, the last 23 bits of the IP address will be the other 23 bits of the MAC address. And then there's always a 0 in the 25th bit. Okay. So it looks confusing, but it's really not. You've got 01005E. So if the address is 239.255.1.1, and that is the multicast address and that you're going to use to join the group, your host would also listen on the MAC address that is 01005E7F0101. And that is achieved by taking the last 23 bits of the IP address, converting them to hex, and flipping that 23rd bit. The 23rd bit is always, well, 25th bit, sorry, 25th bit is always 0. And then the last 23 bits are the bits of your IP address. So 239.255.1.1 ends up being 01005E7F0101. Okay. There are 32 multicast addresses that are not unique because they actually convert to the same number for the MAC address. They overlap. So, and that's one of the things here. Here shows an example of 239.255.1.1 and 239.127.1.1 end up giving you the exact same MAC address and the same for the MAC address for the multicast stream. So just be aware there are those 32 that overlap. Okay, so it is a known issue because of the way they are designed. So for that reason, many programs will try to stay away from those. So how do we make sure that only hosts that are supposed to get the multicast get it? Well, we use Internet Group Management Protocol, and that allows users or receivers, and by the way, those who receive the multicast are called a receiver. They can send an IGMP join request. And if the networking devices understand IGMP, they will then understand that, hey, I have a device on that segment or on that port that needs to get information for IGMP in this IP address, and this MAC address is on this port. There are different versions, IGMP version 1, which is not used anymore, IGMP version 2, which only supports unknown source addresses for multicast streams, and then IGMP v3, which does support actually sourcing the multicast stream. Okay, so there's a single source is only supported by IGMP v3. IGMP v2 supports multi-source, or it supports any source. It's called any source. Okay. So here is a message format for IGMP2. I don't think you're going to have to worry too much about the format. Just notice it does have a time to live of 1. That way, it's only processed by the local router, not forwarded. You can have different types of messages. You can have reports. You can have leave groups. One important thing about a leave group is when the last member of a group leaves, the device will then remove that multicast group from its IGMP information and will no longer send things out that port. So if you want to receive a stream, it sends an unsolicited membership report, commonly called a join, to local router saying it wants to join. Let's say it's 239.1.1.1. The router then sends that upstream using PIM, which is the Protocol Independent Multicast, basically a routing protocol for multicast that's riding on top of other routing protocols. And then that will begin the process of creating a pathway from the source down to the destination. We will find out here in a little bit how that takes place, but again, if you want to leave, it sends a leave to the all routers group, and then it will actually remove it. The big thing about IGMP v3 is that it is backwards compatible with all of them, but it does have the ability to set up what is called source filtering. And it can say basically, I only want to get streams from this source list, or it can exclude sources. So you can say, I don't want traffic from any of these sources, but I do want them from these sources. So it's a way to actually include the source, which could let you be more diligent about where the traffic's originating. And then with switches, we have a thing called IGMP snooping. IGMP snooping allows the switch to look at devices and see if they are in fact part of a multicast group. And if they are not, then it can quit sending multicast out that port to them. So there's two ways you could do it. You could do it with IGMP snooping, or you could do it with static MAC address entries. You don't want to do static. That's just too much work. So use snooping, and snooping will allow you to automatically not flood traffic out ports that don't have a device on it. So here we see here IRC 4541. It looks at the join messages, and then it will figure out the multicast MAC addresses that are on those interfaces. Okay. And then any frame that comes in, a stream that comes in for that particular MAC address, will only go to the interfaces of the devices that are in fact part of that group. If they're not, it will not send it out to anybody else. It won't send it out at all. In fact, if, let's say, workstation A leaves the group, then gig 00 would be removed from being associated with this MAC address of 7F0101, and traffic from the stream would no longer go out gig 00. So with IGMP snooping, we can actually control all the way out to the actual endpoints, pretty much, whether or not a stream gets sent to that device. Now, in order for all the devices in your network to know that a stream needs to go from a source to a destination, we need a way to route multicast. And the multicast routing protocol is PIM, Protocol Independent Multicast. It's the only one Cisco fully supports. It is a multicast routing protocol that sits on top of a unicast routing protocol. So it will not work without a unicast protocol underneath. So it's going to be referencing our normal protocols, OSPF, EIGRP. It's going to be referencing those internal gateway protocols for its path determinations. But then it will use those to create the PIM routing information on top of that for multicast. There's two ways it's going to define the path, either a shortest path first tree, or there's going to be a thing called rendezvous point trees. You're going to create a rendezvous point. You can either manually set that rendezvous point, or you can have it be an auto random rendezvous point, and you'll create a tree from there. And we'll talk about those here now. So here's your source tree. It's a distribution tree where the source is the root of the tree. The branches form a distribution down to the receivers. When it is built, by default, it will use the shortest path from the network source to the leaves of the tree using the routing table of the unicast protocol that's riding underneath PIM. Okay. And this is called an S, G. So S, G source group. And you'll see our notation here saying basically to get from the source 239.1.1.1, we're going to go from the source of 10.1.1.2 to 239.1.1, go down 10.1.2, and then down to the receiver. Now, the way this works by default, again, there's no switches that we can see in here, so there's no IGMP. So by default, everyone in the both sections off of R3 and R4 would see this stream that comes through. They have to process it at least up to layer 2, looking at that MAC address for the stream, And if it doesn't apply to them, it would chuck it. Okay. And we're going to be able to do things to fix that, like IGMP and other things. But and we're going to be able to run PIM in a different mode later. But this is just the base, creating a source tree using shortest path first. Okay. If you're using the rendezvous point method, okay, what you end up doing is you end up with what's called a star comma G. You end up with a rendezvous point, okay, and that is where all of your multicast sources go to that rendezvous point, and then it becomes the main forwarding area for all of the other points in the tree. So star comma G, and you can manually do this, or there is an auto RP protocol that is proprietary to Cisco. There's a non-proprietary one too, but the one we're going to talk about is mainly proprietary. So we'll notice some terminology you need to kind of know. First hop router, that's the router closest to the multicast source. Then we have possibility of rendezvous points inside of this. And then the last hop router is the last router that deals with the multicast before it is delivered to a receiver, which would be the multicast receiver. Okay. Now, one of the things you see here is this RPF interface, reverse path forwarding. The RPF is used, the way RPF is figured is by finding the best path using the underlying unicast protocol back to the source. The RPF, the join that is used by that, makes sure that that there's no loops. Basically, it will stop a loop because you're only going to use the best information. And what happens is this: you're not going to send it back out an interface from which you learned the route to get there. Okay, so that reverse path forwarding will stop that. So we won't end up with loops going on. And there's actually I'll show you a picture of it later to make more sense. So there are 5 modes that we can deal with. Dense mode, sparse dense, multicast, source specific, and bidirectional. So let's talk about, first off, some PIM control messages. You know, they use IP protocol 103. All PIM routers, the address is 224.0.0.13. By default, we send out hello messages every 30 seconds. All right. And then if it is a multi-access link, there is a way to do de-election, and that is just to ensure there's not so many different multicasts going out on a multi-access network. So dense mode. Dense mode follows what is called flood and prune operations. So what it does first is it floods the multicast traffic throughout the entire network. And then as they receive it, all right, they use reverse path forwarding, okay, or filtering, reverse path filtering, to figure out the best path back to the multicast source. And then if it's a non-RPF interface, and you'll notice what happens here, you notice how the multicast source, it got down to R3 from both R1 and R2, but R3 will not forward information back that way because that's not the best route back to the multicast source. And that is learned via the unicast protocol that these routers are running, right? So by default is packets will arrive to all of the routers first, okay? And then once it figures out that only R3 has receivers, it will eventually, if you tune it correctly, prune out the non-multicast segments, okay? Now, the problem is, since it is flood and prune, it is, once the topology is all good, you'll notice it prunes it out here because it's not going to use RPF. But eventually what's going to happen is it's going to end up creating this multicast source, and R3 will still send it over to R4. And it will still go out here even though there's no receivers, because by default, every single area where there is a link, it's going to end up creating a tree to it and sending it there. Okay. Even though there's no receiver on R4, it can go out over there. Because dense mode is It's very resource intensive because it is flood then prune. We don't recommend it in production environments, okay? What we recommend is sparse dense mode. And now sparse dense mode, it can work for, it was designed originally for when there's a group of multicast clients or receivers that are spread throughout the network, but it can also work when it's very densely populated. It does use that unicast routing table to perform the reverse path forwarding checks. It doesn't care what the routing protocol is, as long as there's an underlying routing protocol, even if it's a static route. It uses what's called an explicit join model, where the receivers will send an IGMP join to their router so that it will become a last hop router. And then it will send a PIM up toward the source to create that tree. That forwarding state is only done based upon those explicit joins. So it's different in flood and prune. In dense mode, it is assumed everyone's going to join. In sparse mode, it's not. It's only those explicit joins that create the leaves on the shortest path first tree. So here we have, and also another thing about sparse node uses rendezvous points. Okay, that's one of its main delimiters too. But you see here, first hop router then sends a multicast traffic to the rendezvous point, which makes the multicast source known. All right. And then, now one interesting thing about this is the following. When this multicast starts, okay, the very first packet will go through the rendezvous point. But after that first stream goes to the rendezvous point, that last hop router then typically will begin to use the best path back to the multicast source. So to do the first route, the first packet or couple packets will go through the rendezvous point. And then since there's a better route up to the multicast source, it'll switch over after that. Okay. So that's what this switchover mode is. So the very first join will go explicit join. Receiver A says, I want to join this. Last hop router will send information to go to the rendezvous point. We'll create a path up to the multicast source. The very first couple packets will go down through the rendezvous point. Once that is done, then it will immediately, after that first multicast packet, it'll go back to the shortest path first. Okay. So to go back to the shortest path between R1 and R3, instead of going down through R2. Okay. So if this link fails, it would go back here, but just realize that is not the shortest path. It's used to create the initial connection. But then after that, the last hop router is going to use the best path using those forwarding first hop routers. Okay. If we have a LAN segment, we don't want duplicate multicast traffic on the LAN. So we create a designated router, kind of like we do with OSPF and LAN segments. The only negative here is by default, all DR routers in PIM mode have a priority of 1, which means the highest IP address on the subnet is going to be used to become the DR. So if you don't want that to be the DR, you need to manually change the PIM DR priority. So again, this reverse path forwarding is an algorithm used to prevent loops. So if it receives a multicast packet on the interface, it uses to send unicast packets to the source. It has arrived on the RPF interface. If it arrived on a interface that does not use for sending things back to the source, it will discard it because it's seen as a loop. So again, basically what this means is it won't use a secondary route unless the primary route fails. And that's at RPF, or reverse path forwarding check. And ensures we don't end up with duplicates. And here's an example. You'll notice that R2 and R3, they're sending, here's multicast coming down. They both send information to one another. But R3, when it gets that information from R2, is going to ignore it because it has a path directly through R1 up to the multicast and vice versa. Okay. Now, rendezvous points in sparse mode is mandatory that you choose one or more routers to be out rendezvous points. You can even set up multiple rendezvous points, one for X number of streams and one for another set of streams. It can be done statically, or you can let it be done with auto RP. There's also a thing called PIM bootstrap router, but the best way to do it is by static. Set your rendezvous points statically so that you know where they are and you know what streams they are going to handle. So what set of multicast IP addresses they're responsible for. You can use Cisco's proprietary auto RP, and it will try to load split. It will also try to place it as close to the group participants as possible. It's can do a good job, but let's be honest, I'll be honest with you, I've never worked with auto RP, so I don't know how good a job it does. I get scared with things that are auto mechanisms because I've seen them make dumb decisions before. But just be aware it's there and it is available. So this just talks about how a candidate RP advertised its willingness to become an RP with 224.0.139, which is the announce. And then if there are multiple ones, the one with the highest IP address will become the RP. So if you don't manually set it, it's going to be the one with the highest IP address in the in that particular area of your network. It's going to become the rendezvous point. And this is the non-proprietary method in RFC 5059, which is the bootstrap mechanism. It is very similar to what is used by Cisco's auto RP, but it's an open standard. Okay, it is part of the PIM version 2 specification, so just be aware you can actually use that if so needed. Here we have an example of this BSR mechanism where they're doing candidate RPs and coming possible rendezvous point for these different sections. Okay, everybody, that's multicast. It's not a massive topic on the exam, but it's something you need to know about. It is something that shows up in real world networks. I've had to help some people with multicast on occasion, but it's not a topic that is going to cause you too many headaches. I think the big thing is remember PIM uses your underlying routing. If that routing is not working, PIM's not working. Many times I've seen the problems with PIM not be PIM at all. The issue was simply the underlying routing protocol was wrong, or there was a problem with the routing of the routing protocol. And so be aware the underlying unicast routing protocol has to work before PIM will work. And if that's working, then PIM should work fine once you configure it. Okay. Now I want to talk a little bit about quality of service. Not going to spend a ton of time on quality of service, but I want to talk just a little bit about it. The big thing about quality of service that we need to think about is quality of service. This is one thing that almost never, ever leaves the edge of your network. So this is almost always internal unless you somehow, again, encapsulate it inside of some type of tunnel and tunnel it between two different sites. Once you leave your network, quality of service is out the window. It's not going to follow the packet outside of your network 99.9% of the time. But be aware there are needs for it, especially when we look at things like voice traffic, anything, video traffic, anything that needs to be delivered without delay or jitter or with packet loss. So quality of service, we need to, one thing, first off, by the way, one way to fix these issues is not to install quality of service, but just give your stuff more bandwidth. If you for some reason have 100 megabit links on your network anywhere, get rid of those, go to gigabit, go to 10 gigabit, go to 40, whatever. If you cannot add more bandwidth, then of course quality of service becomes an option that you can use. The QoS models that we have, one is best effort, which is no QoS. And that's just, it's going to go, get there if it gets there. And it's using all the mechanisms of TCP/IP for getting there on time, in sequence, and intact. There is another one called integrated services, where applications tell the network to make bandwidth reservations. That can be a bit overwhelming to your network. And we'll see that in just a second. And then there's diffserv, and diffserv allows you to classify traffic and then tell your devices what to do with that traffic based upon the classification. Now, IntServ was created for real-time apps like voice and video. It uses the resource reservation protocol, and it is used, as you will see right here, to make a reservation throughout your entire network for traffic. So centers on the left side are trying to do a one-to-one bandwidth reservation to each host on the right. So RSVP will send path messages to the receivers, and all of those receivers across will attempt to make a reservation using what is being requested via RSVP. And so every single one of these will try to reserve the amount that is being requested. So in this case, you'll see that 10.111 to 10.331 asks for 64K, which is typically plenty for a voice call, by the way. But 10.113 is asking to go to 10.333 and asking for a 256K reservation. So each one of those can do this independent reservation, but it has to, every device in the network has to speak RSVP, has to understand IntServ, and has to be willing to do those reservations. Okay. Then as data goes through hop by hop, it uses it. Now that uses a huge amount of processing power on your devices, and a lot of RSVP messages and reservation information to keep these things up to date. So every single node has that state. Okay. If any node in the path doesn't understand RSVP and IntServ for some reason, your quality of service is out the window. Okay. Now, you've got to run a RSVP protocol for IntServ to work. All your devices have to target. Every device in the path has to understand it. Diffserv tries to strike a balance. Okay. There's no need for a signaling protocol, so it's more scalable. Each characteristic is on a hop-by-hop basis as they look at how they are designed to handle the classification. So each device in the hop will be told how to handle each piece of traffic due to its classification. Okay. Problem with diffserv is it's not end-to-end quality of service because it can't guarantee enforcement. It's enforced on a hop-to-hop basis. Whereas with IntServ, it's on a complete basis. It's on a path basis. So IntServ is end-to-end. Diffserv is not. Okay. So it's still, though, better than best effort. But be aware, it's not considered an end-to-end solution because it's not carrying that information all the way through the network. It's each device makes its decision based upon the classification of the data. So we take the traffic, we have to categorize it, and then based upon your business requirements, tell all your devices in your network what to do with it. And so we can mark, remark, and queue all of the traffic, and I'm just going to go down. It can be done many different ways. It can be done based upon the IP addresses, ports it comes in, DSCP, you probably heard of that, differentiated service control points, which are can actually go all the way out to an IP phone. They can understand DSCP, IPP, IP precedence, and source destination IP addresses. Those can all be used to classify data. TCP UDP ports can be used. NBAR 2, or you may have heard of NBAR, but NBAR 2, which lets you actually recognize up to 1,000 applications. And as that data comes in based on the application, you can give it a quality of service on a device based upon that classification. Okay. Good thing about NBAR, like they said, is you can, as NBAR is updated, you may not have to upgrade the iOS on the router or even reload it for it to understand it. But you mark it, and marking can take place typically by some type of tagging. Okay. Obviously, you have 802.12q tags. We've talked about those with the VLAN tagging. But you also can use inside of here, there is a field that's not just used for VLAN ID, but in the 802.1q tag can be used for priority code point, and it can be used for quality of service. So that 802.1p field that's part of the 802.1q header can be used for quality of service. So you can tag it with the VLAN and tag it with quality of service. Here's some of the different priority code point settings. 0, lowest, is background, which basically means it is the least important traffic you have. 1 is best effort, so kind of like it's get there if you can or can't. Excellent effort is 2. 3 is critical application. Okay, so it's something that's important, but it's not as important as something that is time sensitive or latency system. Latency enabled, okay, or latency is an issue for it. PCP value 4 is where we get to the first video with less than 100 millisecond latency and jitter. PCP 5 is less than 10 millisecond, which is internet, which is voice VO. 6 is network control, and then the highest is our network control. So anything that's actually required for our network control would be given layer 7 or 7 PCP priority. Okay, so those are bits that are inside of this 802.1q header. If you use this, though, if you use PCP and it travels through any link that strips the 802.1q tag, you lose all of your quality of services, your class of service. You lose every bit of class of service as soon as that VLAN tag is gone, because you lose your PCP tag. Okay, so be aware of that. That means everything has to maintain that 802.1q tag all the way out to where you want it to be, and then once it's delivered to the end device out that switchboard, you can remove the tag, but that's the last place. So everything in your network has to support it. So if you think about this, if you have a network that is routed out to your buildings, you're going to lose those tags. So this would require that your quality of service, or your class of service, would only work out in your edge buildings. Because as soon as it's converted to layer 3, you're going to lose your VLAN tag. Because we're not trunking between buildings when we have a layer 3 set up with our buildings. So just be aware of that. Okay. Now, we can use layer 3 marking. And that is a little more, it's better because it can actually traverse other than trunk links. Okay. So we can use a diffserv field here, or DSCP field, differentiated services control point field can be used. And that is a way of doing it to make sure it's layer 3 classification, not down at layer 2. We then can set up per hop diffserv behaviors. So you can actually tell it what to do. You can tell it to, best effort, guaranteed, expedited. So all of these are ways of taking your diffserv, we'll just say diffserv, DSCP, but your diffserv information and acting upon it and setting it to where it will be a particular thing. So here's our different precedences, okay, under the diffserv field. And again, we go down through, and it really goes through just talking about assured forwarding and weighted read and all of those. Basically, what it comes down to is we have a way for traffic to be classified, and in that classification, we can tell it whether or not it's drop eligible, when it should be dropped, what traffic should get precedence over other traffic. But all of your devices in your network have to support whatever quality of service method you determine to use. Okay. And because of our layer 3 networks now, we're probably better off going with diffserv than we are with others, depending on where that trust boundary is. And that's what this is talking about here, where the quality of service boundary is and where that will take place. So you have to be very careful with that. All right. And again, here we have policy and shaping, talking about what to do, creating committed information rates, committed burst rates, token buckets. All of these are algorithms on how you can figure out When information will be promised to be delivered, the committed information rate, and what will be our burst rate, what it can go above that committed information rate, and anything above the committed information rate is typically drop eligible. So you have to be careful with that. That if you set a committed information rate and your traffic goes above that, anything above it can be discarded. And that means it can get kicked out of the bucket and thrown away. Okay. See if there's anything else I really want to go through here that's kind of, all these are just looking at how buckets work. Yeah, that's just describing that. So no, all that's pretty much, obviously, you know what first in, first out is, FIFO, weighted round robin, low latency, all those are just ways of doing queuing, different types of queuing. These are all latency queuing. Our more current one is class-based weighted fair queuing. So it's queues based upon 256 classes. And then low latency queuing takes that class-based and combines it with priority queuing. So, all right. Big thing I want you to take away from the quality of service is, remember, whatever method you pick, it has to be supported by everything in your network. And it doesn't survive going outside the network. So when we have networks that don't support quality of service and we try to send quality of service information across it, it's removed and all that hard work you did is gone. Okay. Any questions? Any problems with labs? Well, one thing, let me warn everybody again. I won't, Jim. I'm going to send it to you. I promise. I am sorry it's taking me so long. We can also, if you want to hang out here when we're done, I'll talk to you a little bit about it. But we'll talk about it. But other thing I want to remind everybody is, don't forget, when you do your labs, make sure you do a delete VLAN.dat and restart and reload your switches before you start your labs. Some things are surviving reboots, so please make sure you do that, and we'll make sure that happens. Okay. So make sure you actually do and delete the VLANs, erase the start, and reload it. Okay. All right, everybody, I'm gonna stop the recording.